let's start by summarizing all the distributions that we covered in the last hour. What's one of them? The Bernoulli distribution, the Bernoulli random variable. Very simple random variable. How many values does it take? 1 and 0, so 2 values. It takes the one with, value 1 with probability p, 0 with probability 1 minus p. How many parameters does it have? Just one parameter. That's p. The probability of success, if you will. Okay. What's the next one? Binomial distribution. A geometric. Okay. Number of times my friend takes the driver's license test until he passes. Okay, so the number of trials up to and including the trial on which we get the first success. Okay, and it has one parameter only, that's p. Okay, it's okay, again, it's integer valued. Its support is infinite. Okay, it takes all values from 0 up to infinity. Okay, what's the next one? The binomial. Binomial is the number of successes in n independent Bernoulli trials with probability p, of success p. Okay, so it has two parameters, p and n. N is the number of attempts. P is the probability of success in each attempt. Okay, you can express it in terms of the sum of n independent Bernoulli random variables. And finally, different from all of these, we defined the Poisson random variable, which has this PMF. The probability that x is equal to k is lambda to the k e to the minus lambda divided by k factorial. It may be looking a little confusing at first, but it has just one parameter, lambda, and we argued without any proof that it's similar to the binomial. The binomial will converge to the Poisson under certain conditions, and we'll learn a lot of nice properties of the Poisson distribution. Its support is also infinite, just like the geometric, from 0 up to infinity, integers from 0 up to infinity. Okay. Are there any questions with on these things? No? Okay. The next distribution is a discrete uniform. The discrete uniform random variable takes a number of values, consecutive integer values, with equal probability. Okay, so x is a discrete uniform random variable in the interval a to b, where b is bigger than a, if and only if px of k is equal to 1 over the number of numbers in this interval, b minus a plus 1. Okay, let's plot this. So, x is uniform in the interval of integers a to b means px of x is constant from a plus 1, a plus 2, up to b. Okay? It takes all integer values in this interval with equal probability. That probability is, well, 1 over the number of values, which is 1 over b minus a plus 1. Okay? So, is the Bernoulli distribution ever uniform? When? P is a half. When P is a half, the Bernoulli distribution is uniform. It takes the values 0 and 1 with probability 1/2. It fits in with this description, okay, with this definition. Right. So here's another example for you. I roll a four-sided die. What's a four-sided die? Our tetrahedral die, right? I roll this die. Let x be equal to the outcome. Okay, 1, 2, 3, 4. Okay. Is x a uniform random variable? Example. So x takes the values, what? 1, 2, 3, and 4 with equal probability. 1/4 each. Is this uniform? Yes. Okay. What? Four-sided die. Okay. Yes, you're right. If it's not fair, then this curve, this figure will not be true. Okay. But let's add the word fair. Okay? A fair four-sided die is rolled. How about y is the outcome divided by 3? Okay, so y is 1/3, 2/3, 1, or 4/3. It takes these values with equal probability. So can we say that y is uniform? So y is 1/3 with probability 1/4, 2/3 with probability 1/4, and 3/3, which is 1 with probability 1/4, and 4/3 with probability 1/4. So it takes 4 values with equal probabilities. Can we say that y is a uniform, discrete uniform random variable? So it takes the value 1/3 and 2/3 and 1 and 4/3. No, right? When I sketched it, the people kind of realized it does not fit into the definition of a uniform random variable. Why? Because it doesn't take all integer values from one starting integer to the from some a to some b. It just takes values that are arbitrarily placed between the value 1/3 and the value 4/3. So it doesn't really fit into this description. I mean, yes, it takes equal, it takes 4 different values with equal probabilities, but it doesn't really fit into our definition of a discrete uniform distribution. A discrete uniform distribution has only 2 parameters, A and B. Okay? So how about this? Let z be equal to the square of the outcome. Square of the outcome. Again, is z uniform? So z takes the values 1, 4, 9, and 16. So z is 1, 4, 9, or 16 with probability 1/4, 1/4, 1/4, 1/4. Is z uniform? No. Okay. How about that? How about the following? Q is this, let's see, twice the outcome of the die roll. Twice the value of the die roll. So this time, Q takes integer values, right? 1, right, 4, and 6, and 8. Does it have a uniform distribution? No. Okay, how about this? P, now let's use another letter. R is x plus 2. Is it uniform? So let's check. R is 3 or 4 or 5 or 6. Okay. With probabilities 1/4, 1/4, 1/4, 1/4. Yes, this is uniform. Okay. Okay, any questions about the discrete uniform distribution? No? Okay, so let's move on. Sometimes we take a function of a random variable, f of x. Okay. The random variable x is already a function itself, right? What's it a function of? It's a function defined as a mapping from the sample space to real numbers. Okay. Once we take another mapping from x to y, provided that's a valid function, the random variable, this new thing y that we define, will continue to be a random variable. Example, let x be the temperature in Celsius. Okay, so we have a certain probability distribution for the temperature in Celsius, but we would like it in Fahrenheit. Okay, so you know, there's a simple linear conversion from y to x to y. Y is 1.8 times x plus 32. Okay. Now everything, if we know the probability that x is bigger than or equal to some value, can we compute the probability of y being greater or equal to any value? Yes. If we know these probabilities for x, it's easy to compute them for y because there is a one-to-one mapping from this event, y bigger than or equal to 14, to this event. So let's write this. Probability that y is bigger than or equal to 14 is the probability that 1.8x plus 32 is bigger than or equal to 14, right? But this is nothing other than x being bigger than or equal to what? Minus 18 over 1.8. And provided you know the answer to this in terms of x, you can compute the answer to this in terms of y. So what does this say? A function of a random variable is another random variable. Okay? Example. Another example where we can compute the PMF. Let x be a uniform random variable between -2 to 2. Okay? It's passed through a transformation. Y equals the absolute value of x. What is the PMF of y? How do we do this? What's your name, please? Yes. Emre. What possible values can Emre, can y take? Eylem. Eylem? Erdem? What are the possible values that y can take? What is y? So x is x. Excuse me? Between 0 and 2. Positive values. You're right. Yes. So x, in the example, x is uniform from -2 to 2. Okay? Then y, which is the absolute value of x, will take the values 0, 1, and 2. What is the PMF of x? Let's plot the PMF of x. Px of x. It's between, so basically it takes how many values? Emre, how many values does x take? 5, right? Okay. So it takes -2, -1, 0, 1, and 2. Okay? So are these constant? Are these values constant, Emre? Yes. What's the height here, Emre? 1/5. Yes. Now let's do the same for y. Py of y. Now it's going to take the values 0, 1, and 2, right? How do we go from px of x to py of y? Let's remind ourselves the definition of py of y. Py of y, the PMF of y, is the probability that y is equal to the value script y. Okay. So what is the, for example, py of 0? The probability that y is 0. We don't know that, but we know x, right? This is the probability that the absolute value of x is 0, which is the same as saying, what is the probability that x itself is 0? 1/5. Okay, so we got that. 1/5. In fact, that came from here. What's next? What is py of 1? Right, that's the probability that absolute value of x is 1, which is the same as saying that x is either 1 or -1, which is the probability of x being 1 plus x being -1. 1/2 plus 1/2. 2/5. So that's 2/5. And it comes from the sum of this weight, this mass, and this mass. Similarly, the probability that y is 2 is the probability that x is either 2 or -2. And the probability of that is again the sum of this probability mass and this probability mass, which is 2/5. Okay? So this transformation took the first PMF and shuffled the weights around, redistributed the probability masses to get another valid PMF, which is different. Okay? Any questions about this? This is also called a derived distribution. We derived the distribution of y from the distribution of x. Okay. No questions, Emre? Okay. What's your name? Berkin. Any questions? No? Okay. So, okay, so let's try to sort of generalize what we did here. So, let's see. Y is g of x. Okay, y is g of x. And to find the probability py of y, find the PMF py of y, we can sum px of x over all values x such that g of x is y. Okay? Let's see that we understand this. This is the probability that y takes on the value y. Y takes on the value y whenever big X, the random variable x, takes on the value x such that g of x is equal to y. So for all small x values that map to small y, okay, if we sum the probability masses of those values, okay, we get the probability mass at this value y. Okay, so here's another example. There's a uniform random variable which is uniform from -3 to 3. Okay, it's passed through a transformation. Y equals u of x. Let's ask this to Erdem. U of x. Yes. Handouts. Oh, I'm sorry. The handouts are kind of. We ran over the handouts at this point. Huh? Okay. What is u of x? U of x, well, it's the, as you can read here, it's a discrete unit step function. Okay. Let's ask someone else. Maybe you can't see very well from over there, kind of squeezed. Yeah. So what happens when we take x, the random variable x, and pass it through the discrete unit step function?
If x is positive, then y is 1. If x is negative, then y is 0.
Nice. Okay. What happens if x is 0? Okay. So maybe we need to define that. It may not be a standard definition. Let's take that as 1 also. Okay? So it maps all values between -3 to 3 to just two values, 0 and 1. Okay, let's write this here. Basically, previously, px of x was uniform from -3 to 3, okay, and its PMF was constant. How many values? 7, right. This was the PMF. Let's compute the PMF for y, py of y. What's the PMF for y? What is the support of y? What's your name? Yes. You, yes. Best friend of Erdem. Berna. So Berna, how many values does y take, Berna? Yes, good. So Berna, what are the probability masses at those values?
Y takes 0 when x is 3.
Correct. And we can add 0 also to those if we define unit step function to take the value 1 at 0. So that would be excellent. Yes, 4/7. And this would be then 3/7. Good. Okay, so this PMF has been mapped to this PMF by this transformation. Okay? So for this value, I summed up, these. Oh, no. What did I do? It's completely wrong, right? This should be 0 must be 3/7. And this should be 4/7. So for this 3/7, I summed up these weights. And for this 4/7, I summed up these weights. Okay. Any questions? Okay. So, expectation and variance. Okay. Expectation and variance, maybe let's skip the mean for now. Expectation and variance are two very important and two very frequently used, okay, functions of a random variable. We are sometimes interested in, rather than getting the full PMF, okay, on some summary information about the PMF of the random variable, such as what is its average value? I mean, which value is it expected to take? For example, instead of comparing your grade, the grade you get from an exam, with every single person in the class, you often compare it with the class average, right? Because class average to you is a useful statistic. It sort of tells you, what the average person did. Okay, so it's a useful statistic of the distribution of grades that people got from the exam. Okay, the expectation comes from that idea. Okay, here's an example. And again, you could consider it as a probability puzzle. Okay? A fair die is thrown in a casino. Okay? If 1 or 2 shows, if the result is 1 or 2, the casino will pay you a net amount of 30,000 liras. Okay? If 3, 4, 5, or 6 come up, they will take the money you put down. Okay, whatever the money you put down was. Up to how much would you put down to play this game so that you would expect to break even? Okay, so I'll let you think about this problem. Since we ran out of the lecture notes do not come up to this point. Let's stop the lecture here. And we'll continue next time.